creep. We have discussed about in the previous modules about how a material behaves under cyclic loading. A material can fail at a stress well below the static tensile or yield strength if it is subjected to cyclic loading, because damage gets accumulated during this cyclic loading, and upon repetition or over a lengthy period of service the material undergo fracture, so which is fatigue, which are known as fatigue failures. And another cause of failure which takes place at very high temperatures, as well as certain high temperature applications, when a component is subjected to a constant load, the component undergoes time dependent plastic deformation, and over a lengthy period of time eventually leads to rupture. So this time dependent plastic deformation at constant load and at higher temperatures, at temperatures greater than 0.3 to 0.5 of the absolute melting point, it is known as creep. Normally at low temperatures, metals and most of the alloys, metals and alloys, the limiting design factor is the yield strength for low temperatures. But as the temperature increases greater than to about 0.3 to 0.5 of the absolute melting point, the mechanical strength of the material, it is limited by creep rather than its yield strength. So therefore this creep is an important consideration in many high temperature applications. Example of the high temperature applications where the turbine, most of the turbine components which are subjected to high temperatures, as well as power and chemical plants. So all these are subjected to very high temperatures. So thereby the mechanical strength of these components, it is limited by creep, not by its yield strength. So even though the loads or the stresses are well below the yield strength, static yield strength, these materials, they undergo plastic deformation with respect to time at higher temperatures. Whereas at low temperatures, time is not a factor. Whereas at high temperatures, plastic deformation increases with time at constant load and at higher temperatures. And moreover, at high temperatures, when one compares the mechanical properties of materials, because the mechanical strength, it is related to its melting point, thereby the ratio of test temperature to that of melting point, which is expressed in degrees Kelvin, it has to be used, which is known as homologous temperature. And moreover, it is also advisable if one compares the flow stress of two materials at an equivalent homologous temperature. So it is advisable to use the ratio of sigma by Young's modulus rather than flow stress alone, because at higher temperatures, or temperature is having an effect on Young's modulus. Thereby, if one compares the flow stress of two materials at an equivalent homologous temperature, it is better to use this ratio rather than simply the ratio of flow stress, because temperature is having an effect on Young's modulus. So in the creep, when we say about the homologous temperature, it means it is a ratio of test temperature or the operating temperature of the component or the test temperature of the component to that of its melting point. This is expressed in degrees Kelvin. So this is the homologous temperature. So creep, it can be defined as time dependent deformation at constant load and at higher temperatures, at elevated temperatures. So for most of the high temperature applications, this creep is an important consideration or important factor to be considered, because most of the applications, elevated temperatures or high temperatures applications. So if one needs to select a material for such application, they have to conduct some experiments, some tests to evaluate the long-term elevated temperature service of the component. Next, at higher temperatures, the movement of the atoms, it is more pronounced. Thermal energy leads to the vibration of atoms, the movement of atoms. It is more at higher temperatures, and it enables the rearrangements in the structure to take place. Also, at higher temperatures, there are many processes which comes into the picture. One is the diffusion controlled mechanism becomes operative. Number of slip systems will increase with increase in temperature. Slip becomes easy. Dislocation annihilation takes place, whereby the density or the number of dislocation comes down, as well as dislocation climb, by which the dislocation movement take place, which is a diffusion controlled process, as well as the concentration of vacancies also increases at higher temperatures, whereby this dislocation climb becomes easy because it is controlled by two processes. One is diffusion and another is some vacancies are also required for this climb to take place, whereby the vacancies also increases. The concentration of vacancies increases at higher temperatures. So all these processes, they lower the strength of the material at higher temperatures, as well as oxidation and intergranular attack. It is also a problem at higher temperatures. When a component is exposed to a very high temperature in air which contains oxygen, oxidation and intergranular attack is also a problem. So at higher temperature, the metallurgical stability of the component, it is a big issue, because all these processes which takes place at high temperatures, they cause lowering of the mechanical properties, lowering of the strength of that material, as well as degradation of the material takes place at high temperatures. Because creep is an thermal activation process, plastic deformation can take place with time, even though the stresses are well below the yield strength of the material. Whereas this is not observed at low temperatures, because the stresses to deform the lattice, if the stress to deform the lattice, it should be greater than that of the yield strength. Whereas at the case of high temperatures, the stress to cause plastic deformation even though it is well below the yield strength of that material. The material undergoes plastic deformation because of this thermal activation, whereas the stresses to deform the lattice are more, that is, it is greater than that of the yield strength without thermal activation. Creep behavior, it occurs in any metals or alloys in the temperature range between that of 1/3 to half of its absolute melting point. That means the onset of creep takes place in most of the polycrystalline metals and alloys at temperatures between 1/3, that is 0.3 to about 0.5 of the absolute melting points. So in order to determine when a material mechanical strength or the mechanical properties they are limited by creep rather than yield strength, one has to conduct some experiments in order to evaluate the long elevated temperature service. In order to evaluate the long-term elevated temperature service, as well as in order to find out the temperatures at which the mechanical properties of the materials or the strength of the material, mechanical properties or the mechanical strength of the material, it is limited by creep. It is limited by creep rather than its yield strength. One has to conduct some experiments. It has been seen that for low melting point materials like that of lead and tin, low melting point materials, the onset of creep takes place at room temperatures or slightly above room temperatures, whereas for some of the materials like nickel based super alloys which are used for very high temperature applications, these materials are known to retain their strength even at higher temperatures. So for these type of materials, nickel based superalloys as well as some refractory materials, it has been found that the onset of creep occurs at temperatures greater than 980 degrees centigrade, whereas for the case of low melting point materials like lead and tin, the onset of creep takes place at room temperature or else at slightly above room temperature. Slightly above room temperature. So for a specific material or a specific alloy or specific metal, tests have to be conducted in order to find out this transition where the mechanical strength or mechanical properties, they are limited by creep rather than the yield strength. So the type of tests that are conducted in order to evaluate this long-term elevated temperature service of the component as well as where this transition occurs. There are two types of test. One is known as the creep test and second is known as the stress rupture test. So one is known as the creep test and second is the stress rupture test. So the creep test, it is conducted on a specimen at an elevated temperature at constant load, and with respect to time, the strain that is accumulated, it is determined. So creep test is based on to evaluate the time dependent strain which occurs at constant load and at elevated temperature, whereas stress rupture test, which is carried out at very high stresses, at very high stress, at elevated temperature, and the total time required for rupture of the specimen is determined. Here we determine the rupture life, that is time to cause rupture. At higher stresses, various tests are conducted. That means tests are conducted at various stresses at elevated temperature in order to find out the time to cause rupture of the material. And creep test, it is conducted to find out the strain that occurs in the material due to the constant load at elevated temperature with respect to time. So this creep test, the duration of this creep test, for a shorter duration, it can be of about 6 months, which is considered a shorter duration to conduct the creep test. 2, for a long duration, it can take to about 10 years. So creep tests, they are conducted for shorter duration, which occurs to about 6 months, to that of a long duration where it may take to about 10 years. Whereas stress rupture test, it can complete to about 1000 hours. Here the stresses are very high, and at elevated temperature, what is the time to cause failure is determined. Here the strain versus time, what is the amount of strain with respect to time, it is determined by means of this creep test. So this creep test, the schematic view of this creep test, it can be as follows. In a furnace, we have 2 heating elements. So here the specimen, which is at constant load at a temperature, at a constant temperature, where these are the heaters which maintains a temperature, and this is the chamber. So to this specimen, which is gripped at one end, and to the other end loads are attached. So the specimen, it is under constant load, and this tensile specimen, what is the amount of strain it accumulates or it undergoes with respect to the high temperature and with respect to this constant load, that is determined. So this is a form of creep test in order to find out the strain that is accumulated in the material with respect to the constant load and that of the high temperatures. Because for this high temperature applications, creep is one of the important factors that is to be considered, because it undergoes, the component undergoes time dependent strain even though the stresses are very low, that is well below the yield strength. So it is a problem of dimensional stability of the component. So when it undergoes deformation with respect to time, that means when it undergoes creep at elevated temperatures, so the dimensional stability of the component is lost. So this is one of the important consideration for very high temperature applications where creep is to be considered, as well as the material, it undergoes not only the changes in dimensions with respect to temperatures, but for a prolonged period the material may undergo rupture. It eventually leads to rupture for some period of time. So from this experiment, from this creep test, strain is determined with respect to time. A plot of strain with respect to time is plotted, and it can be seen that the curve, this is a generalized creep curve which is found for certain combination of stress and temperature, where here we have an instantaneous strain which occurs upon loading, then slowly the strain decreases with time. This is the first stage, and this is the second stage, and this is the third stage, where finally the material undergoes fracture. So creep rate, it is indicated by epsilon dot, that is creep with respect to time. So this is a generalized creep curve which shows three distinct stages. So this is the initial elongation that takes place, and then you can see that the creep rate, that is the creep rate, it decreases with time, and then the creep rate, it is almost constant, and then finally here the creep rate increases rapidly and the material undergoes rupture. So these are the three distinct stages in the case of a creep curve, where the same curve, it is not seen for all the materials, for all the metals and alloys, but it can be seen for a particular combination of stress and temperature. Now we shall discuss about the different stages of creep. The first stage, second stage and third stage, which is followed by this instantaneous strain. The primary creep, the first stage creep, stage 1, is known as primary creep, which is also known as transient creep. Primary creep or transient creep, where following an initial elongation, the creep rate decreases with time. The creep rate, it decreases with time following with an initial elongation. The competing process of strain hardening and recovery takes place. And then this is the second stage, where the creep rate is minimum, where the creep rate is essentially constant. It is sufficiently constant, and it is referred to as minimum creep rate. So this primary creep rate or transient creep or primary creep, it represents a stage where rearrangement of crystal imperfections takes place. Following this rapid elongation due to thermally activated plastic strain, crystal imperfection rearrangements takes place. The competing process of strain hardening and recovery leads to a stable dislocation configuration. So this is about the stage 1, or which is also known as primary or transient creep. And the second stage, this is known as secondary creep, where in the case of stage 1, the processes, competing process of strain hardening and that of the recovery processes leads to a stable dislocation configuration. It leads to stable dislocation configuration following this rapid strain, following this instantaneous strain which occurs due to thermally activated plastic strain in the component. Then the stage 2 is where the creep rate is constant, essentially constant at a minimum rate, and it is known as minimum creep rate. So the creep rate in second stage, it is known as minimum creep rate. So this is known as minimum creep rate, where the creep rate is essentially constant at a minimum rate, so it is known as minimum creep rate. For very high creep resistant alloys, the creep rate, this minimum creep rate, is essentially constant and it is also known as steady state creep rate, which is indicated by the subscript S, that is known as steady state creep rate, where the minimum creep rate value is steady and it is known as steady state creep rate. So this is one of the important design parameter that is considered in designing a creep resistant material. So this can be related to the rupture life, time to cause rupture. So the portion of this secondary creep, it occupies a largest portion in the creep curve, and this is the important design parameter in designing the creep resistant materials. So steady state creep rate, or the secondary creep, where the creep rate is minimum, which is known as minimum creep rate, it occurs mainly due to the competing processes, that is the strain hardening and recovery. These processes, strain hardening and recovery, these two processes balance. When there is a balance between the strain hardening and recovery processes that take place in the case of stage 2. So the changes during stage 2 with respect to the microstructure can be explained as follows. On an atomic scale, the number of dislocations increase, thereby the density of dislocations increases and the strength of the material increase. That means the material undergoes strain hardening, as well as at high temperatures the number of dislocations, they rearrange and annihilate, thereby the dislocation density comes down. Recovery processes occur and strain hardening is relieved. At still lower temperatures, the creep rate, it further decreases to a lower value because strain hardening is dominant. When there is a balance between strain hardening and recovery, the creep rate is at a minimum rate, which is known as minimum creep rate. Most engineering applications for high temperatures, it falls in the range between 0.4 to 0.6 absolute melting point. So within this range, 0.4 to 0.6 of the absolute melting point, it can be, the creep process can be related to that of an Arrhenius equation. So the creep rate, the steady state creep rate within that temperature range, 0.4 to 0.6 of the absolute melting point, it can be related to Arrhenius rate equation, where it is given by minimum creep rate is A sigma whole to the power of n into e to the power of minus q by RT. So this is an power law expression where creep rate is related to the key variables that are temperatures, temperature and stress. So creep rate, it is related to the variables temperature and stress by this equation, where A is pre-exponential constant, n is also a constant, and R is universal gas constant, and T is the temperature. So creep rate, minimum creep rate, it is related to stress and that of the temperature by this equation. But when the stresses are very high, creep rate is very rapid, and this power law does not hold at such high stress region. Thereby, that region is known as power law breakdown, where this power law is not valid when the stresses are very high and the creep rates are very rapid. So that is known as power law breakdown. So from this equation, creep rate, which is related to stress and temperature within this range of temperature. There is a correlation between the activation energy for creep and that of the activation energy for self-diffusion for the case of pure metals. And it has been found that they are closely related. The activation energy for self-diffusion, the activation energy for creep. It has been found that the activation energy for self-diffusion is closely related to that of activation energy for creep for most of the metals. Self-diffusion means diffusion among similar atoms in a matrix. The minimum creep rate, it is the important design parameter, that is the minimum creep rate in the second stage. It is an important design parameter. So there are two criteria. One is the stress to produce 1% strain in 10,000 hours, and the second criteria is stress to produce 1% strain in 1 lakh hours. So this criteria, it is used for jet engines, and this criteria, it is used for steam turbines. So these two are the common criteria, and minimum creep rate is an important design parameter that can be obtained from the secondary creep. The first and second stage creep, it can be related by means of an empirical relation which is given by Garofalo. The empirical relation, it is with respect to the strains. So the total strain is equal to the instantaneous strain which occurs upon the application of load, and this is the transient creep. Epsilon T is the transient creep into 1 minus e to the power of minus RT plus minimum creep rate in the second stage. So this is an empirical relation for the case of primary creep and that of the secondary creep. So this is the instantaneous strain followed by the creep rate which decreases with time in the first stage and the minimum creep rate. So epsilon T, it indicates the transient creep, 1 minus e to the power of minus r, where 1 by r, it is related, it is the transition time between the first stage and that of the second stage. It is a transition time between the first stage and the second stage, and epsilon dot 2, it is the minimum creep rate in the secondary creep. So this can also be represented by means of a figure. This is strain with respect to time. So this figure indicates the decomposition of this individual strains. So total strain is equal to the minimum, the creep rate in the second stage plus epsilon naught, this is the instantaneous strain, plus epsilon T into 1 minus e to the power of minus RT. This is the transient creep, which is the first stage. So this is the figure which shows schematically, graphically, this equation given by Garofalo, empirical equation which relates the primary and that of the secondary creep. Decomposition of the strains can be seen from this figure. So when the creep rate, it is plotted with respect to time, creep rate, when it is plotted with respect to time, we have this type of curve. Initially, in the first stage, the creep rate decreases with time. Then it reaches to a sufficiently constant, and then creep rate increases. So this is the first stage where the creep rate following an initial elongation, the creep rate decreases with time. Creep rate decreases with time, and then this is the minimum creep rate. It's the second stage. In the second stage, where the creep rate, it is sufficiently at a minimum rate known as minimum creep rate, sufficiently constant at a minimum rate known as minimum creep rate, and this is the third stage where the creep rate, it increases with time. So this is a plot of creep rate with respect to time. So during creep, secondary creep, significant microstructural changes takes place. On an atomic scale, the number of dislocations increase, and dislocations are forced to move through the material, through the crystal. Thereby, it leads to strain hardening, where the dislocation intersection takes place and leads to strain hardening as the density of dislocation increases. And at higher temperatures, the dislocations rearrange and annihilation of dislocation takes place and leads to recovery. So stage 2, it is a balance between these two competing processes, strain hardening and recovery. So next is the tertiary creep. That is the third stage creep, where the creep rate rapidly increases with time and finally leads to rupture. So this tertiary stage creep, it can be related to that of metallurgical instabilities that takes place in that material. It is due to the metallurgical instabilities that take place in the specimen and the material. Metallurgical instabilities like necking takes place, microvoids, they form and they grow, as well as precipitation of brittle phases which occurs at the grain boundaries. Precipitation of brittle phases at grain boundaries takes place, as well as dissolution of the strengthening phases, which contributes to the strength of the material. So all these takes place. Recrystallization of the strain hardened grains also takes place. So all these processes which occurs in the third stage of creep, that is a tertiary stage. Because of this metallurgical instabilities that takes place during the third stage, the creep rates are very rapid and finally leads to the rupture. In many creep resistant alloys, the deformation, this tertiary creep occurs due to the inherent deformation of the material, which is less than to about 0.5% strain. The minimum creep rate is an important design parameter that can be derived from the creep test, as well as the duration of tertiary creep is also important, because if one can determine the duration of tertiary creep, then the component, before it leads to catastrophic failure, that can be inspected. Because in the case of tertiary failure, necking, all the metallurgical instabilities which takes place and finally leads to rupture. So this failed component can be predicted by knowing the time to rupture, the duration of the tertiary creep, and then catastrophic failures can be avoided. And mostly in the creep test, initially there is an instantaneous elongation. Following this instantaneous elongation, we have time dependent strains. That is, in the case of stage, we have different stages, stage 1, stage 2, stage 3. Following this instantaneous elongation, we have time dependent plastic strains in the component. But in these stages, the epsilon naught, that is the instantaneous elongation, it is not considered in these stages. So this is acceptable for the case of research purposes, but for the case of the designing of components for application purpose, this has an effect. This has to be considered, because this instantaneous elongation, it accounts for a small amount of strain for the total strain. So this instantaneous strain, it accounts for a small fraction of strain in the total strain, and therefore this instantaneous strain, it should not be eliminated, or it should be considered for the design purposes, because it also accounts for a small fraction in the total strain. So this should not be neglected while designing the components against creep. Moreover, creep tests, they are conducted at constant load and at constant temperatures, at some elevated temperature which is constant. But rarely in service, the parameters, they are not constant. And with increase in stress and with increase in temperature, the creep rate increases. This can be seen from this figure. With increase in stress and with increase in temperatures, the creep rate increases. This is for temperature less than 0.4 of the absolute melting point. This is T1, T2, T3, sigma 1, sigma 2, sigma 3. With increase in temperatures, T1 is less than, T2 is less than T3, sigma 1, sigma 2 is sigma 3. So the creep rate increases with increase in temperature and also with increase in stresses. Next we will discuss about the stress rupture test. Creep tests, they are conducted at constant load rather than constant stress, because at the constant load, the material undergoes time dependent deformation at high temperatures. As the specimen undergoes elongation at constant load at high temperatures, the length of the specimen increases and cross-sectional area decreases. So as the cross-sectional area decreases, stress increases, because stress is equal to load by the cross-sectional area. Thereby, the creep tests, they are conducted at constant load rather than constant stress. Now, in the stress rupture test, which is conducted at high stresses when compared to that of creep test, so the test can be completed to about 1000 hours. The time to cause rupture for a material it can be concluded, this test can be concluded within this time, which is less when compared to time required to complete this test, to conclude this test. It is much less when compared to that of creep test, which takes about several months. That is the shortest duration, whereas it can go to a duration to about some 10 years, which is the long duration. So moreover, for the case of constant load, tertiary stage of creep is seen, whereas in the case of constant stress, tertiary stage is not seen. And the total strain in the case of stress rupture test, it can be to about 50% strain, whereas in the case of creep test, the strains are less than to about 0.5%. So these are some of the differences between stress rupture test and that of the creep test. So when the stress rupture test, it is carried out for various stresses sigma with respect to time at various temperatures. Time to rupture is determined. So this is for an elevated temperature T1, T2, T3. So tests are conducted at for a constant stress, some high value of stress at various temperatures, where T1 it is less than, T2 is less than T3. T3 is at a high temperature. So you can see from this graph that when the temperatures are very high, then there is a rapid change in slope. There is a rapid change in slope. This rapid change in slope, it is due to instabilities, metallurgical instabilities, which we shall discuss in detail later. So this is about the stress rupture test. Which is conducted at various constant stress at various elevated temperatures. T1 it is less than, T2 is less than T3. T3 it is at very high temperature, and it can be seen that at this high temperatures there is a sharp change in slope, which is due to the instabilities present in the material, metallurgical instabilities. So in the case of stress rupture test, stress rupture ductility, it is one of the important parameter. Stress rupture ductility, it is one of the important parameter that is to be considered if the components, they contains stress concentrations, notches as a part of design. This is one of the important parameter, because at high temperatures the ductility of the material, it is decreased due to the stress concentrations, notches, etc. So in order to evaluate the stress rupture ductility from the creep test, two types of elongation measurements are important. One is the true elongation, and second is the total elongation. In order to evaluate the stress rupture ductility, the elongation, two types of elongation measurements, these are determined from the creep test. The one is true elongation, which is the elongation up to the second stage, elongation up to the second stage creep, and where total elongation, it is up to rupture, elongation up to rupture. It is the elongation up to rupture, and this is the elongation up to the second stage. It means upon the completion of second stage, till second stage. So these two parameters are important in evaluating this stress rupture ductility. So when true elongation as well as total elongation, it is plotted for the case of an material at various temperatures, it has been seen that the total elongation, it is subjected to more scatter when compared to true elongation. So this is elongation when it is plotted. This is true elongation and this is total elongation. Similarly for this, it is total elongation and this is true elongation. This is for the case of cobalt, chromium, nickel base alloy with respect to the rupture life. Two different temperatures, 730 and 925. It has been observed for the case of an alloy which is tested for the two different temperatures. So when elongation which is determined, that is total elongation up to the rupture, and true elongation, that is upon the completion of the second stage. So when this elongation for this alloy, it is plotted with respect to rupture life for two temperatures, different temperatures, it has been found that this total elongation, it is subjected to more scatter with increase in temperature, more scatter with increase in temperature than that of true elongation. The reason why total elongation it is subjected to more scatter than true elongation is because of the microstructural instabilities, the instabilities that occur in the tertiary stage, the metallurgical instabilities, microstructural instabilities which occurs in the tertiary stage. So this is the reason for this increase in scatter with respect to temperature for the case of total elongation. Whereas in the case of true elongation, that is up to the elongation up to the second stage creep, where this microstructural instabilities or microscopic instabilities, they are not seen in the case of secondary stage. So this stress rupture ductility, it is important in the alloy selection for high temperature applications. So this stress rupture ductility, which is important for high temperature applications, which can be seen from this figure. So based on this stress rupture ductility, alloy selection can be made. An alloy which is having a high stress rupture ductility, it is selected when compared to that of alloy which has a low stress rupture ductility, because this the alloy which is having a low stress rupture ductility, it cannot be used up to its full strength potential. So this is the safety margin. This is the safety margin for the case of an alloy which is having a high stress rupture ductility, and this is the safety margin. This is the safety margin for the case of an alloy which is having a low stress rupture ductility. This is strain and this is with respect to time, and this is the creep design, where here it leads to rupture. This point indicates rupture. So this stress rupture ductility, it is important in design of creep resistant materials, because an alloy which is having a high stress rupture ductility when compared to that of an alloy which is having a low stress rupture ductility, this alloy which is having a low stress rupture ductility, it may fail during the tertiary creep. That means it may leads to premature failure during the tertiary creep because of lack of ductility. So this is useful in selecting the alloys. the minimum creep rate in the secondary stage creep, it can be related to that of minimum creep rate or steady state creep rate. It can be related to that of rupture life, that is time to cause failure. So there, among the various relationships, Monkman and Grant has given a relationship which relates minimum creep rate and that of the rupture life. They are inversely related. Log of rupture life plus log of minimum creep rate is equal to a constant. So from this, one can evaluate the rupture life knowing the minimum creep rate.